Hello, this is Sarah Bonner, and this is the first asynchronous video prior to the first class for EDPS 722 Tests and Measurement at Hunter College. So when you start the construction of a test to measure something, you will start, as we are going to discuss in the first class, with the construct that you intend to measure. But when you start actually the mathematical components of the measurement process, you start with numbers because all measurement involves numbers. So this is going to be a little bit of reacquainting you with the way that numbers act in measurement, which is more constrained than they act than the way they act in measurement. So numbers as measurement are different from the way they are in their pure form, in that they represent something. 2 is a number. 2 is 1/2 4. 2 is 1/4 of 8. It has no unit attached to it. When you start to talk about 2 units of alcohol, then that is a measurement of a certain of alcohol. But what is a unit of alcohol? Well, if you look it up, actually, a unit of alcohol is defined differently in different countries. So the 2 units of alcohol, okay, so as a number, 2 always equals 2. As a unit of alcohol, 2 units of alcohol in the United States does not equal 2 units of alcohol in Britain. That was actually a good example. Didn't expect it to be. So some numbers in measurement are not like regular numbers, and you need to know what they're like in order to know what you can do with them. What they're like, their qualities as numbers, are not as unlimited as they would be if they were pure numbers. Now, famous article, one of my favorite articles by Frederick Lord, called "The Numbers Don't Know." Once you have written down, okay, how many units of alcohol do these various people drink a day? 2, 3, 0, 4, 1, 0, whatever, the distribution of units of alcohol consumed. You can do anything mathematically that you want to with them. The numbers don't know that they're measurements, but it's really important that you know, because if some of those 2s are on the British system and some of those 2s are on the American system, then your 2s don't all mean 2. They don't all mean the same thing. So it's very important that you know what kinds of measures you are dealing with and what is permissible and not permissible given. And what level of, we say, of measurement you're dealing with, it has to do with the construct. Certain constructs, which are have more linearity than others, lend themselves to some kinds of numerical representation, and others don't so much. So we're going to start with the simplest form of measurement, which is just to take a group and divide its members into categories. So take a distribution of values and or to take a quality and group characteristics that separate cases according to the quality. So that's called nominal measurement, also categorical. I use both terms pretty much interchangeably. And when you are nominally measuring something, nominal means name only. The only information that the value that you give to the attribute conveys is what category it belongs to, is its name. It doesn't tell you how good it is, how bad it is, how strong it is, how weak it is, where it stands relative to other categories, above, below. The only thing that it tells you is that it doesn't equal another category. So if a case X is in category I, then it's in category Y. It only has two choices related to category Y. It could be in category Y, or it could not be in category Y. It can sometimes partly be in category Y and partly be in category Z. If X is in category Y, then it cannot be in category Z. If X is not in category Y, it could be in category Z. So you can only belong to one. So that's what you know when you know someone's or what the nominal value is of a case. If you know what category it's in, it doesn't tell you anything about value, rank, weight, anything like that. The only statistics that you can run or use with categorical memberships are frequencies. You can count how many cases fall into a given category. Percentages, you can translate the frequencies into percentages. Relative percentages, you can that's percentages, I'm sorry. You can report the mode, the category that occurs most frequently, and you can do contingency table analysis, which includes your chi-square. So that is a kind of statistical test, inferential test. It's not a parametric test. It doesn't rely on the normal distribution. You have no really expectation because nominal measurement isn't a scale. You have no expectation of the normal distribution. As Stephen said in 1946, anything goes with the nominal scale, has no distributional expectations for one thing. The paper by Stevens from 1946 that's cited here is kind of interesting because what it shows you, which I was surprised the first time I ever saw it, is that there used to be considerable debate on scales of measurement and how many different scales there were. And that debate, it's turned into a mere convention. Most people agree that there are these 4 scales. There are problems with this as a method for describing levels of measurement, but it works reasonably well. The next level of the levels of measurement, next type of levels of measurement is the ordinal measurement. And ordinal measurement is rank order. And on this scale, the category that a case belongs to not only indicates what it is and what it isn't, but it indicates where it stands in relation to the other categories above or below, greater or less. It carries transitive properties. So if say that, well, you have here with the example on the slide, kind of letter grades. A is greater than B, B is greater than C, therefore A is greater than C. So if you know case 23 in my distribution has a B, you not only know what you would know with nominal measurement is merely case 23 has a B, that means it doesn't have an A and it doesn't have a C. With ordinal measurement, you would know that case 23 has a B, which means that it's lower than cases with an A, and higher than cases with a C. So you know something more. You know where a case ranks relative to others. The fancy way of saying this is that ordinal measurement has monotonic increasing functions, which is that as values increase on the scale, then the level that is measured also increases. That there's no place where there'll be a dip. So for instance, let's add a letter grade in here, D. A is greater than B, B is greater than C, C is greater than D. It isn't going to be that D, in fact, is greater than A. That would not be that 4, 1 is less than 2, 2 is less than 3, 3 is less than 4, and then 4 is greater than 2. 4 is less than 2. Screwing up the analogy again. And don't believe I can draw this. I can draw sharing. Okay, so since I was confusing about that, I'm going to draw this out. This is a monotonically increasing function. So you've got an increase. You may flatten out the slope for some way, but it's still going to increase. It may increase at different rates of increase, but it increases at all points. This is non-monotonically increasing or non-monotonic function. Not even, you call it increasing, it doesn't always increase. Maybe it starts out by increasing, and then it actually takes a dip. And then it increases again and take another dip. So that's not monotonic. It doesn't always move the same direction at all parts of the scale. This always moves in the same direction upward at all parts of the scale. Okay, so I'm sorry I had to make that little digression, but I had led to created a confusion. With ordinal measurement, you can calculate medians. You can do all the things you could do before, modes, frequencies, percentages. You can also do medians, percentile ranks, and there's some tests that you can do that are based on the median, such as the Wilcoxon sign rank test, which are tests of, rather than mean comparisons, median comparisons, because you